In June 2017, geologist Marie Jackson and her collaborators at UC Berkeley and the University of Utah made a groundbreaking discovery. They published a paper in American Mineralogist, which quietly solved a riddle that had puzzled experts for over 2,000 years. The team drilled concrete cores from submerged Roman harbor structures at Portus Casanus, located on the Tuscan coast. These piers, continuously soaked in the Mediterranean since the reign of Augustus, had stood the test of time and their concrete was still strong. Jackson and her team ran these cores through electron microscopes and synchrotron X-ray beams at Lawrence Berkeley National Laboratory. What they found shouldn't have been possible. Inside the matrix of the concrete, an unusual mineral, a luminous tobermerite, was still forming, growing and interlocking, plate by microscopic plate, after 20 centuries underwater. Modern marine concrete is engineered to last 50 to 100 years. After that, the steel rebar corrodes, the matrix decays, and the structure must be replaced. But the Roman piers defied this logic. The longer they sat in salt water, the stronger they became. The sea didn't destroy them. It became the ingredient that strengthened them. This discovery wasn't just an exciting find. It was the beginning of an entire rethinking of ancient construction methods, showing that the secrets of the Romans were much more advanced than we had ever realized. Now, to understand this discovery, we need to step back to a single building that has been quietly humiliating modern construction for almost 19 centuries. In Rome, there stands a circular temple completed around the year AD 126 under Emperor Hadrian. This temple, known as the Pantheon, was converted into a Christian church in AD 609, which is one of the main reasons it survived when most other ancient temples did not. The Pantheon's dome spans a remarkable 43.3 meters, about 142 feet, and has stood for almost 2,000 years without a single steel reinforcement bar, retrofit anchor, or tensioning cable. Today, it remains the largest unreinforced concrete dome on Earth, larger than St. Peter's, larger than Florence Cathedral, larger than anything we've managed to pour without metal. The Romans had two ingredients that we no longer commonly use. The first was pozzolana, fine volcanic ash mined near Pozzuoli, just outside Naples. The second was hot quicklime, used in a way that modern textbooks had dismissed as sloppy and unscientific. For nearly 2 centuries, as of January 2023, the judgment was completely overturned by MIT. The Roman architect Vitruvius, writing around 25 BC, had recorded the working ratio of 1 part lime to 3 parts pozzolana for above-ground work, and 1 to 2 for anything submerged in seawater. Vitruvius didn't fully understand the chemistry behind it, but he documented a practice that worked. The piers at Portus Casanus and the breakwaters around the Bay of Naples, built with the same method, still stand today. None require maintenance, none have been repaired, and the concrete remains chemically active. In the most precise sense, it is alive, continuously strengthening itself even after all this time. To understand the full impact of Jackson's findings, we need to travel about 13 kilometers east across the Mediterranean to the city of Constantinople. Founded by Constantine on the European edge of the Bosphorus in the year 324, Constantinople was expanded under Theodosius II in the early 5th century. By the time the Visigoths sacked Rome in 410, the imperial government in Constantinople was watching the collapse of the Western Roman Empire unfold in real time. In response, they built walls. Not just any walls, but the Theodosian walls, a 4-line defensive system that stretched 5.7 kilometers from the Sea of Marmara to the Golden Horn. These walls included a flooded moat, a breastwork, an outer wall 8.5 meters tall and 2 meters thick, and an inner wall 12 meters tall, reinforced with 96 polygonal towers rising up to 20 meters above the parapet. But the engineers of Constantinople had no Vesuvius, no natural volcanic ash. So they invented an artificial pozzolan. They took fired clay bricks, ground them into a coarse powder, and mixed that brick dust with slaked lime, river sand, and rubble aggregate to form the mortar core. The chemistry was identical in principle to Vitruvius's original method. The reactive silica and alumina in the fired clay locked onto the calcium hydroxide in the lime, growing crystalline calcium silicate hydrate gel through the rubble. The horizontal red bands that you can still see across surviving sections of the wall in modern Istanbul are not decoration. They are structural seams, designed to dissipate seismic shock and bond the limestone facing onto the mortar core. For more than 1,000 years, that wall did its job. When the Avars failed against it in 626, the Arab Umayyads failed in 674 to 678, and again in 717 to 718. The Bulgarians, the Rus, and the Crusaders of the Fourth Crusade all tried and failed. Every army that approached Constantinople by land broke against the Theodosian system. Earthquakes in 437, 447, and 740 cracked sections, but the city quickly repaired the damage and the walls held. Then, in 1453, Sultan Mehmed II arrived with 60 to 80,000 troops, more than 300 ships, and a piece of artillery without precedent in the medieval world. This artillery piece was a bronze bombard, cast by the Hungarian engineer Orban. The cannon, nicknamed the Basilica, was 27 feet long, with 8 inches of solid bronze barrel walls and a bore 30 inches across. It fired stone balls weighing roughly 12 pounds, and the sound of its discharge could be heard 10 miles away. For 48 days, from April 11th to May 28th, Orban's gun and dozens of supporting cannons hammered the wall. But the wall didn't behave like stone. When 540 kilograms of granite slammed into the dense earthen and ash matrix at terminal velocity, the projectile didn't split the wall the way it would have shattered a granite block. Instead, the matrix deformed. Locally compacted particles slid against each other, absorbing the kinetic energy and redistributing it through the rubble core. Each shot eroded the cannonball nearly as much as it eroded the wall. The defenders patched breaches overnight, using timber, earth-filled barrels, and wool bales. By morning, the patched section of wall behaved exactly like the original mortar. The Theodosian walls were never breached by force. The city fell on May 29th, 1453, but not because of the walls. Late in the final assault, a small postern gate called the Kirkoporta was found unlocked. A unit of janissaries poured through, and the defenders, outnumbered roughly 10-1, were overwhelmed in close combat. The city was lost, but the walls, the mortar that absorbed Orban's 12-pound stone shot, remained standing. The Basilica cannon cracked apart from its own discharge and sat silent on the morning the city fell. The mortar that withstood it was made of 3 things: dirt, lime, and powdered fired brick. The same 3 categories of material that built the Pantheon's dome 1,000 years earlier. The same 3 ingredients that lined the harbors at Pozzuoli, where Marie Jackson's team is still drilling cores today. The same materials that built the lime-plastered houses at Aşıklıhoyuk in central Anatolia, 9,000 years before any of the others. This was not a hidden secret of the ancients. The chemistry was figured out before writing even existed. If this material is so good, if it absorbs cannon fire, ignores earthquakes, and grows stronger over 2,000 years of salt water, then why did the world abandon it? The answer is not some grand conspiracy or a buried secret. There's no shadowy memo hiding the truth. Instead, the reason we stopped building with these ancient materials is rooted in industrial economics, a perfectly clean story of market forces that explains every step of how lime pozzolanic construction was displaced. In 1824, an English bricklayer named Joseph Aspdin patented a process for grinding limestone and clay together, firing the mixture and grinding the resulting clinker into a fine powder. He called it Portland cement. 20 years later, Isaac Johnson refined the kiln temperature to produce true modern Portland clinker, and by 1920, it was being manufactured on an industrial scale across Europe and North America. By 1930, Portland cement had become the default global binder for construction. The lime pozzolan tradition that Vitruvius and the Theodosian engineers had used was, in less than a human lifetime, almost entirely displaced. What Portland cement offered wasn't better engineering, but a better business model. Lime pozzolanic methods required time. Rammed earth and lime mortar cures slowly over months and years and gains strength continuously across decades. Portland cement, on the other hand, reached roughly 70% of its design strength in 28 days. For a developer building a 30-story tower, that difference is not just a technicality, it's the difference between a profitable project and a bankrupt one. The ingredients for lime pozzolan construction are scattered across local geology and waste streams. Portland cement, however, is manufactured in centralized factories, bagged and shipped worldwide. Its predictable performance allows for uniformity in the global construction industry, which relies on standardization. Portland cement formulas can be patented, branded, certified, and standardized. This is something that simply didn't exist for the older method. Not because anyone forbade it, but because no one had a financial reason to build with it. This isn't a conspiracy. It's market selection. Portland cement won, not because it was better for building, but because it fit the economic needs of 20th century construction. But as the cost of carbon emissions has become clearer, so too has the environmental toll of Portland cement. Modern Portland cement production accounts for roughly 7 to 8% of global carbon dioxide emissions, about 1.6 billion metric tons of CO2 in 2022, with a trajectory toward 3.8 billion tons per year by mid-century. About half of those emissions come from the chemistry itself. When limestone is calcined at over 1,400 degrees Celsius, it releases CO2 as a byproduct, regardless of how clean the energy source is. The other half comes from the heat itself. In contrast, a lime-stabilized rammed earth wall has roughly 1/10 to 1/5 the embodied carbon of an equivalent reinforced concrete wall. The earth requires no firing. The pozzolan, when it's wood ash or rice husk ash, is already a waste product. The lime requires firing, but at lower temperatures and in much smaller quantities. And it absorbs CO2 back out of the atmosphere over its lifetime through carbonation. This isn't a moral argument. It's an engineering argument with real implications for anyone planning to build, retrofit, or maintain a structure that will outlast their grandchildren. The shift in material use wasn't just about better engineering or durability. It was about the economics of the supply chain. The materials that made up Roman concrete were abundant, local, and inexpensive. As long as we continue to prioritize economic optimization through mass production and centralization, we will continue to choose materials that are less sustainable. But the materials the Romans used, which have stood the test of time for over 2,000 years, are right beneath our feet. With some time, effort, and the right knowledge, we can rebuild with them and build structures that will last for centuries rather than decades. In 2017, the discovery made by Marie Jackson's team answered why Roman marine concrete continues to strengthen underwater. But that still didn't explain why above-ground Roman concrete also had the remarkable ability to self-heal when cracked. That answer arrived in January 2023, when a paper published in Science Advances by Admir Masics at MIT, working alongside Linda Seymour, Daniel Mora, and collaborators from the Weiss Institute at Harvard, along with laboratories in Italy and Switzerland, revealed the mystery. For decades, archaeologists had noticed small white inclusions scattered through Roman concrete samples, millimeter-scale chunks of bright calcium carbonate. They were referred to as lime clasts. The standard interpretation had been that Roman workers simply mixed concrete poorly, leaving these clasts behind as a sign of sloppy construction. However, Masic's team refused to accept this interpretation. They argued that the Romans had perfected this material over centuries, and they would not have tolerated sloppy mixing on the most important construction projects of the empire. So, Masic's team analyzed the lime clasts using scanning electron microscopy, X-ray diffraction, and Raman imaging. The results told an unambiguous story. The Romans had been using quicklime, the unreacted form of calcium oxide, directly in the dry mix rather than the slaked calcium hydroxide that modern concrete uses. When water hit the dry mixture, the quicklime reacted exothermically, heating up the entire batch. Masic's team called this process hot mixing, and it trapped the lime as small, brittle, and highly porous reservoirs of reactive calcium throughout the concrete matrix. Then, when a microscopic crack opened in the concrete and water seeped in, the water dissolved calcium from the nearest lime clast and carried it into the crack. There, it precipitated out as fresh calcium carbonate, sealing the crack with newly formed crystalline rock. This self-healing process was not just theoretical or poetic. It was measurable, peer-reviewed chemistry, replicated in modern lab samples. Scientists have since run water through cracked samples of Roman concrete and watched as the cracks sealed themselves shut. In 2025, the same MIT team examined raw material piles preserved at an active Roman construction site, frozen in time by the eruption of Mount Vesuvius at Pompeii. They confirmed that intact quicklime fragments were premixed with volcanic ash before water was added. This was precisely the hot mixing protocol that Masic's chemistry had predicted. The walls of ancient Roman structures didn't just survive, they healed themselves. And this wasn't just some ancient lost secret. It's a scientifically repeatable process that could have profound implications for modern construction. This discovery shattered the notion that the Romans had simply stumbled upon a crude construction method. It turns out that their material science was advanced, purposeful, and engineered for resilience. The walls of the Pantheon, the piers at Portus Casanus, and the other structures built with Roman concrete didn't just resist the test of time. They actively fought against decay, regenerating themselves when cracked, just as modern concrete cannot. The knowledge of this ancient process had been forgotten, but it was never lost. Now, through the work of scientists like Masic, Jackson, and their colleagues, we are beginning to rediscover it in laboratories around the world. These findings aren't just academic, they are a powerful tool for modern engineers, offering a glimpse into a past where buildings were meant to last for millennia. The techniques rediscovered in these ancient walls have the potential to revolutionize how we think about construction, durability, and environmental sustainability in the present day.